All right, so graphing trig functions. Okay, as I've been saying for the past couple of lessons, all of your exact values come from the unit circle or the special right triangles. Well, your graphs are going to be the same way. Most of your graphs actually are going to really come from the unit circle. Okay, so remember that on the unit circle, we always start with a rotation that begins at 0 degrees here on the right-hand side. Up top, that becomes 90. To the left, that becomes 180, and on the bottom, that's 270, coming all the way back around to 360. Okay, so what we're actually going to use them in when we put them on a graph is actually in radian measure. So if I took each of these values, remember to convert to radians, we times by pi over 180. So for example, take 90, times it by pi over 180. You're really reducing 90 over 180 to become 1/2, and that's how that becomes something like pi over 2. So the real values we're going to work with here are really 0, 90 is going to be pi over 2, 180 is going to be pi, 270 is going to be 3 pi over 2 if I go through the process that I just did before, and 360 is going to actually be 2 pi. Those are the values that are going to be our 5 key points that we're going to put along the x-axis when we make a sine or a cosine or a tangent graph. Remember, cosine comma sine is each point on the unit circle. Cosine comma sine. Okay, and then I just put these here just in case we have to come back to them for anything a little bit later. Tangent, if you remember, is also the identity sine over cosine, and I'll come back to using that a little bit when I make my tangent graph. Okay, so when you set up your grid for your sine or cosine graph, you want to make sure that you're equally spaced along the x-axis. A lot of times I would do, let's say, 2 boxes or 4 boxes. It's really up to you. Let's say for right now, I'll just do 2 boxes. So I'll go 2 boxes and put pi over 2. Okay, so I'm starting with 0, then I'm going up to pi over 2. Go 2 boxes and then put pi. Go 2 boxes and put 3 pi over 2. And go 2 boxes and put 2 pi. Okay, so most of the time you're graphing on a window from 0 to 2 pi. Okay, because of the fact that we're graphing basically our unit circle points, we're basically only going to be going up to 1 or down to -1. Okay, so starting with sine. Sine is going to be basically graphing all of your y coordinates as you go around the unit circle. Okay, so starting at 0, we have a sine value of 0. At pi over 2, we have a sine value of 1. At pi, we have a sine value of 0. At 3 pi over 2, we have a sine value of -1. Sorry, that's going into the actual number. And at 2 pi, okay, our sine value is back to 0. Okay, so notice the pattern that we just made when we graphed this sine curve, because this is something I'm going to repeat when you go to later graphing for yourself. Starts at 0, ends at 0, goes to 0 exactly in the middle. Halfway between the first 2 zeros, it goes to its highest point. Halfway between the last 2 zeros, it goes to its lowest point. And when you connect those, that makes a basic sine curve. Okay, notice that the domain of the sine curve is basically going to be, I would repeat this graph forever. So my domain for a sine curve is going to be all real numbers. And the range for a sine curve is going to go from -1 to 1. We're going to talk a little bit more about range being changed later when we start stretching and compressing or shifting up and down, because that's going to affect the range. For the cosine curve, we're going to use the same 5 key points. We're going to do pi over 2, pi, 3 pi over 2, and 2 pi. Make sure they're nice and equally spaced. These are the same 5 key points that I get when I rotate around the unit circle. And this time we're going to be graphing our cosine values. So that means you're going to be graphing your x values as you go around. So starting at 0, our cosine value is 1. Okay, so then at the top, at pi over 2, our cosine value is 0. Then at pi, our cosine value is -1. At 3 pi over 2, our cosine value is 0. And at 2 pi, our cosine value is 1. Okay. And that makes your basic cosine curve. So take a look at that pattern. Okay, starts at the top, ends at the top, goes to the bottom exactly halfway in the middle, halfway between the top and the bottom it goes to 0, and that's how you make your full cosine curve. Again, you'll notice the domain is all real numbers for this cosine graph. Basically what happens is as I keep making a larger graph, I'm rotating around this unit circle more, and the range currently is -1 to 1, but as I said before, when we start stretching or compressing or shifting, that's going to end up being a little bit adjusted. Tangent I'm going to need a couple more points for. I'm not going to be able to do it just based on our 5 key points. I'm going to actually need to use the unit circle a little bit. So I'm going to spread this out so I go every 4 boxes. So every 4 boxes, and I'll put pi over 2 and pi and 3 pi over 2 and 2 pi. Okay, but I'm still going up to 1 and down to -1. All right, so let's start with tangent. Again, it being sine over cosine. Let's start with the tangent value that I would get at 0. Okay, so at 0, tangent being sine over cosine would be 0 over 1, would come out to be 0. Okay, so this is where it gets a little weird. At 90, tangent being sine over cosine is 1 over 0, comes out to be undefined. That means it doesn't have an actual value. To represent undefined, we're going to put a dotted line, and you're going to see something called an asymptotic behavior. It's going to approach but not intersect this particular location. Okay, then we go to pi. Tangent is sine over cosine. That's 0 over -1. Dividing by, 0 divided by -1 comes out to be 0, so that's okay. 3 pi over 2, you're going to see some weird stuff happen again. Sine over cosine becomes -1 over 0. Again, comes out to be undefined. Okay, so, and then last but not least, remember that 0 and 2 pi are the same thing, so at 2 pi, we're back to 0. All right, so as we go through, remember our ASTC chart. This is our first quadrant. 0 to pi over 2 is our first quadrant. Okay, tangent will be positive. In the second quadrant, tangent will be negative, so we're going to need a value down here. In the third quadrant, okay, tangent will be positive, and in the fourth quadrant, tangent will be negative. All of those will be tangent of 45, though. So tangent of 45, opposite over adjacent, comes out to be 1. So at 45, we're at 1. Okay. In the second quadrant, when tangent is negative, we'll be at -1. In the third quadrant, when tangent is positive, we'll be at 1. And the fourth quadrant, when tangent is negative, we'll be back down to -1. Okay, so then when you connect these, you don't have to really even be able to graph the tangent yourself. You just have to be able to recognize that this is the tangent graph, that it has asymptotes at pi over 2 and 3 pi over 2, that it's increasing as you go from left to right. That's pretty much it. I'm not going to get too much in the domain and range of this one because it's a little bit weird. I will say the range is all real numbers, but the domain will have to exclude any of these places where I have these undefined values. Okay, really you just have to be able to identify for the stuff I'm going to ask you for. When we get into graphing the reciprocal functions, we're going to see a lot of the idea of like flipping over. What I'm actually going to do with these ones is I'm going to actually start by graphing what the original graph looks like. Okay, and then I'll actually go through and graph what the reciprocal function should look like. So what I'm going to say is cosecant being 1 over sine, I'm going to graph this sine curve that we just graphed before. Okay, so remember we used the point pi over 2, pi, 3 pi over 2, 2 pi. Okay, we went up to 1, down to -1. Here I'm right now just graphing a sine curve. It starts at 0, ends at 0, goes to 0 in the middle. Halfway between the first 2 zeros, it goes to its highest point. Halfway between the last 2 zeros, it goes to its lowest point. And this is what our basic sine curve will look like. Okay, to turn that into our cosecant curve, okay, points like 1 flip over to stay 1, and -1 flips over to stay -1. Points like 0 flip over to become undefined. Okay, and then you just pretty much have to show your graph being kind of flipped over, if you will. Okay, going the exact opposite direction of the way that it was originally curved, but now you have to be careful because now you have this asymptotic behavior that you didn't originally have on the original curve. Okay, so a shape that looks like that is going to be your cosecant curve. Okay, so when it comes to secant, it's going to be the same idea. It's going to be the cosine curve, just flipped upside down. So if I start by making a basic cosine curve, starts at the top, ends at the top, goes to the bottom exactly halfway in the middle. Halfway between the top and bottom, it goes to 0. And that's my basic cosine curve. Okay, places that will stay the same when I start making this into secant, when they get flipped over. 1 stays the same when it gets flipped, -1 stays the same when it gets flipped, and 1 stays the same. 0 turns into an asymptote. Okay, and you again once again do this idea of flipping over. So this curves down, so your secant graph curves up. This curves up, so your secant curve graphs down, and this curves up. Okay, and that's what your secant will look like. So last but not least, we have that cotangent graph. So I'm not going to graph all the points I did before for cotangent. I'm going to just keep pi over 2, pi, 3 pi over 2, and 2 pi. All right, so what's going to happen is that I'm going to start with my basic tangent curve. Tangent starts at 0. I have these asymptotes where it kind of goes up. Okay, and then I have this one where it was an asymptote. Right now, again, I'm just graphing the tangent graph. Okay, when I make this into cotangent, any place that was 1 is going to stay the same, except any place that's 0, okay, any of these zeros are going to become asymptotes now for cotangent. Okay, any of these 1s or negative 1s are going to stay the same. But again, now everything is going to kind of get flipped, if you will. So this is going to go down. Okay, and this is also going to go down. Like I said, you don't have to be able to actually do these graphs yourself. You really just have to identify it. Cotangent and tangent have this shape where they look like, I don't even know, like polynomial graphs, except tangent is increasing, cotangent is decreasing. And then secant and cosecant have these like parabola type shapes. Again, try to match up where like the zeros and the asymptotes are. That's usually the easiest way to find the connection between those graphs. Okay, so we are now going to get into talking about basically trig functions where there are transformations happening, some like vertical and horizontal stretching, as well as we could even talk about some vertical and horizontal shifts, but we're probably going to focus more on the stretching, which is what we call amplitude frequency changes when you talk about them in terms of a trig function. So what you previously had looked at was just a basic sine curve and a basic cosine curve. Think of it like 1 sine of 1 theta, okay? That was an amplitude of 1 because the coefficient was 1, meaning that the highest it went to was 1 or negative 1. And it had 1 in front of theta because we would say that it has a frequency of 1. The frequency is how many curves I would fit in a space between 0 and 2 pi. Okay, so same idea with cosine. It has an amplitude of 1, it goes up to 1, down to negative 1. Again, 1 is really just the distance between what we call the midline and the highest point, or midline and the lowest point. And again, I'm only fitting 1 full cosine curve between 0 and 2 pi. Remember these shapes because these will be important when we start graphing some amplitude and frequency changes. So the first thing we need to be able to do is identify what exactly is this information telling us. So if I have something like 3 sine of 2x, this means I have an amplitude of 3. Okay, how does this change this graph? It's stretching this sine curve by a factor of 3. So therefore, the highest point is going to go all the way up to 3, and the lowest point is going to go down to 3. So the range changes from negative 1 to 1, because I previously had an amplitude of 1, to a range of negative 3 to 3. I'm going to go all the way up to 3 and down to negative 3. Frequency, that's the coefficient of x. The period is 2 pi over the frequency, so 2 pi divided by 2 comes out to be pi. Okay, and then that period is going to tell us how long it takes to make 1 full curve. So that's going to be useful to be able to figure out how big do I have to make each curve so I can fit 2 of them in that window. The domain, no matter what, is going to be all real numbers, so you don't have to worry about that changing at all. Okay? For the next one. So you'll notice now I have a negative in front of that 4. You should know that amplitude is never negative. The negative in the front actually means a reflection over the midline, okay, or reflection over the x-axis. So you're going to see the same kind of curve we had before, except instead of starting at the top, it's going to start at the bottom, but it's going to make that same basic shape as we start making that cosine curve. Because it is an amplitude of 4, once again, amplitude is never negative, the range will go from negative 4 to 4, because it's now being vertically stretched by a factor of 4. The frequency in this case is 1/2. Period is 2 pi divided by frequency, so 2 pi over 1/2 comes out to be 4 pi. So you'll notice that now I'm only going to see half of a curve in the window that I graph. If I needed to make a full curve, it would take 4 pi units for me to do that. Domain is still all real numbers. Okay, so for sine and cosine, domain is always all real numbers, as far as you know right now. Okay, now we're going to graph it. When you are graphing something with amplitude frequency changes, you definitely want to start by doing the analysis I just did before. What's the amplitude? What's the frequency? What's the period? When you set up your graph, you're going to still use your same basic points we did before. I would say go every 4 boxes. Put pi over 2, put pi, put 3 pi over 2, and put 2 pi. I know in the previous lesson I only did 2 boxes. I think when it comes to graphing amplitude frequency changes, it's easier if you go every 4 boxes. They really just have to be equally spaced. So if you did every 3, that's fine too. Okay, so here's 1, 2, 3, -1, -2, -3 to make sure I can fit everything for my amplitude. And now I'm going to start by making my first sine curve. Because the period of these sine curves is pi, it means it's going to start at 0 and end at pi. So a sine curve, if you remember, starts at 0, ends at 0, goes to 0 exactly halfway in the middle, halfway between your zeros goes to the highest point, and halfway between the zeros goes to the lowest point. So it starts at 0. By pi, it's going to end at 0. Okay, so this is the end of that first sine curve. Starts at 0, ends at 0, goes to 0 exactly halfway in the middle. Halfway between my zeros, it goes to its highest point. Halfway between these two zeros, it goes to its lowest point. And there is your first of your sine curves. You should fill the whole window between 0 and 2 pi if that's what you're being asked for. So I'm going to repeat this pattern once again. This time I'm going from pi to 2 pi. So it starts at pi, ends at 2 pi, okay? Goes to 0, exactly halfway in the middle. Halfway between the first two zeros, it goes to its highest point. Halfway between the last two zeros, it goes to its lowest point. And when I connect them, what you're looking at is a sine curve. Okay, so remember the basic sine curve that's been repeated 1, 2 times. That's why it's a frequency of 2, and it's been vertically stretched by a factor of 3. Okay, for the next one, -4 cosine 1/2 x. It is the same basic idea. Pi over 2, pi, 3 pi over 2, 2 pi. Okay? This time we're going up to 4, so 1, 2, 3, 4. Make sure you have enough space. 1, 2, 3, 4. I ran a little bit out of space here, so I added some extra grid. I would definitely make sure that you just give yourself enough space when you have to sketch this. Just print out graph paper. Okay, so one of the biggest things here is that my cosine curve, instead of starting at its highest point, is now going to start at its lowest point. Okay, so it's going to start at its lowest point, end at its lowest point, go to its highest point somewhere in the middle. Okay, so it's going to start at its lowest point, which is -4, based on the amplitude change. Okay, now the thing is, 4 pi would be all the way down here to the right. So somewhere at 4 pi, it's going back to its lowest point. 2 pi is going to be right here, there in the middle of that 4 pi. That's where it's going to get to its highest point. Okay, so notice we're going to, again, only see half of a cosine curve. Here's a regular cosine curve. Here's an upside down cosine curve. We're only going to see this much of it in this window because of the fact that the frequency is 1/2. So it starts at -4, ends at +4, goes to 0 exactly in the middle. And the last thing you have to do is just make sure you get the right curve of that cosine graph. Okay, so I'm going to graph it like this. Oopsies, yeah. It's not the best one, but it'll do. Okay, and that is your -4 cosine of 1/2 x. Okay, applications of trig functions. So now you'll see added into these graphs that I didn't really include in the previous graphs, you have amplitude and frequency changes, and you also have some vertical shifts. So let me talk about how that changes things. Let's say that I had a graph like y equals 3 cosine of x, okay? The amplitude of that graph would be 3. Okay, remember, amplitude is never negative. The original range of that graph would go from -3, I call it original range, -3 to 3, based on the fact that I'm going all the way up to 3 and down to -3. Okay, what if I now made that 3 cosine of x plus 1? That means that I'm shifting my entire graph up 1 unit. That means my range also has to shift up 1 unit. So I'm going to take that plus 1 and I'm going to add that to each side of my original range, and now I get my actual range. Okay, the range of that actual graph comes out to be -2 to 4. So the lowest point this graph is going to get to is -2. The highest point this is going to get to is 4. Okay, we're going to need that because we're going to start answering real-life questions about, sinusoidal curves and things that are modeled by sine and cosine graphs. And one of the big things is what's the highest and lowest point that they get to. The other big thing is what is the period? How long does it take to go through a whole cycle? Is it a wheel rotating? Is it a Ferris wheel going around? Is it a spring bouncing up and down? Okay, how long does it take? That's going to be the period. So I will tell you the frequencies in this case are probably going to feel a little weird. Unlike yesterday where you can be like, oh, okay, I can count up these two curves. You're not going to be able to count up the number of curves. The period is going to make more sense to you. Again, how long it takes to repeat some sort of a cycle. Okay, so we're taking a look at this function right here. So it says amplitude. Remember, amplitude is never negative. So the amplitude would be 3.5, which means the original range would be negative 3.5 to regular 3.5. So that's how high and low this spring is going to go originally. There's a vertical shift. It says plus 7 at the end. That means I'm going to go up 7. So to get my actual range, I'm going to add 7 to each side of that. And this becomes 3.5 is less than or equal to y is less than or equal to 10.5. So that means that when this spring is pulled, as the ball is pulled on the spring, I let go, it's going to bounce all the way between 3.5 feet and 10.5 feet. And it's going to keep repeating over and over. Okay? Horizontal shift. There's nothing added or subtracted inside the parentheses, so there is none. Okay, we're really not going to do a lot with horizontal shifts with these trig functions right now. Is there a reflection? Yes. It means that it's starting at its lowest point, going to its highest point, and then coming back to its lowest point. So visually, this graph is going to look something, actually, you know what? I have a space for the graph. So visually, this graph is going to look something like, okay, so let's say that this is 3.5, and let's say that this is 10.5. This is an upside down cosine curve, okay, so it's going to start at its bottom point, it's going to go all the way to its highest point, and it's going to come back all the way to its lowest point, and we're going to figure out the time frame for that in just a second, okay? So this models the height of that ball on the spring as it bounces back and forth. Okay, so the frequency is the thing that comes in front of the t, so that's 4 pi over 5. Again, I told you frequency is not going to make sense in these problems. You're not going to be able to count up 4 pi over 5 curves between 0 and 2 pi. You're going to use that to figure out the period. Period is 2 pi over frequency. So 2 pi divided by 4 pi over 5. What's nice is that those pi's will cancel, and if you're really bad with fractions, you can type that right in your calculator. 2 divided by 4 over 5. Just use parentheses. Comes out to be 2.5. That says every 2.5 seconds, the ball goes from its lowest point to its highest point, back to its lowest point. So this is a time frame of 2.5 seconds. If you just want to add in one extra time frame right here, right in the middle, half of 2.5 is 1.25. So at 0, it starts at 3.5. 1.25 seconds, it goes to its highest point, and by 2.5 seconds, it comes back to its lowest point. Those are the two main things people are going to ask you. What's the period, and what's either the max or the min? So look at letter C. What is the maximum height the ball reaches? The highest the ball reaches is 10.5, is it feet? Feet. Okay. How many seconds does it take for the ball to return to its starting position? So from 0, it goes all the way to its highest point, comes back to its lowest point. That time to make that full upside down cosine curve is 2.5 seconds. And again, that's the period. So make sure you know how to do the range and the period for these real life questions. So we go on to the next problem. A bay reaches high tide at 8 a.m., which we'll think of as t equals 0, reaches low tide 6 hours later at 2 p.m., which we'll think of t equals 6. Write an equation in the form a cosine of bt plus c, given that high tide is 30 feet and low tide is 12 feet. So we once again are starting at high tide. Okay, so we have a high tide. We're talking about cosine. That's going to be a regular cosine curve. Okay, it says high tide is 30 feet, low tide is 12 feet. Okay, it says that at 8 a.m., which is t equals 0, we start at our highest value and get to low tide 6 hours later. So this is a time frame of 6 hours. How long is it going to take then to get back to high tide? That's going to happen at 12 hours. So what this information tells me is that the period equals 12. Okay, we're going to need the period to figure out the frequency, which is going to be our b value. B value is frequency, which is equal to 2 pi over period. So period equals 2 pi over frequency. Frequency equals 2 pi over period. So I do 2 pi over 12, and that's where we're going to get pi over 6 from. Okay? So we're going to be able to say now that I have y equals something cosine. We now have a frequency of pi over 6t. Okay? And we're going to have to figure out what's our amplitude and what's our midline. So the best thing you can do is figure out what is your midline? What's halfway between 30 and 12? Well, if you add up 30 plus 12 and divide it by 2, you find out that the middle of 30 and 12 is 21. That means that your midline is 21. That is also your vertical shift, so you're shifted up 21 units. Last but not least, amplitude. That's the distance from the midline to the highest point or midline to the lowest point from 21 up to 30. That's an amplitude equal to 9. So 9 cosine pi over 6t plus 21. You needed the period to find the frequency. You needed to find the average of the highest and lowest points to find the midline, which is your vertical shift. And then from midline up to highest point or midline down to lowest point, that's how you end up having your amplitude. At what times in the interval from 0 to 24 does the water reach a depth of 18 feet? Use your calculator and round to the nearest hundredth. Okay, so actually, you know what? I'm going to do the interval from 0 to 12 hours instead of 0 to 24, just to make it a little easier. All right, so first things first, when I graph a trig function, I'm going to have to be in radian mode. Okay, I'm going to be graphing this trig function, y equals 9 cosine pi over 6x plus 21. Okay, the other thing I'm going to be graphing is what I want to be equal to, 18. And the last thing I have to do is I have to adjust my window so I can see this whole problem. So I want to make sure, I'm going to go to my window, I want to make sure I'm seeing from 0 to 12. Okay, so that's going to be my x-min and my x-max, 0 to 12. I also need to make sure that I can see this whole picture. I need to see from 0 all the way up to 30 or from 12 up to 30. That should be fine. I think I'll do 0 up to 30. So my y-min is 0, my y-max is 30. Okay. Oh, did I type something upside down? 9 cosine pi over 6x plus 21. Oh, there we go. Obviously, that just emphasizes the importance of typing stuff in your calculator correctly. Calculator is only as good as what you type into it. I want to find these intersections. So to do that, I'm going to hit second, trace, intersect. First curve, second curve, I've only typed 2 in, so enter and enter. I want my guess to be closer to one point than the other. So just make it closer to the one on the left. It doesn't have to be right on top of it. So this intersects, so visually you're looking at something like this. One graph, t equals 18, and you're finding these intersections. This is t equals 3.649. We want it to round to the nearest hundredth, so that's really t equals 3.65. Okay, and then to repeat, second trace intersect, first curve, second curve, hit enter, and then on the guess, you're just going to move it closer to the second one, and you can see that that's 8.35. Okay, so at what times in the interval from 0 to 12, at 3.65 hours and 8.35 hours is when the tide is going to reach 18 feet. If you want to get really technical, that's like 11:30-ish and whatever 8 hours later than 8 a.m., maybe 4 p.m.-ish, that's going to end up happening. But that's not going to be asked of you. Just give me the time in terms of hours since 8 a.m.